Okay, and it's a pleasure to introduce Mariah Boudreau. One funny thing, and I don't want to ruin the story of the defense you're about to see, but part of the job of doing a PhD is to, do a lot of different things, trying to figure out who you are as a researcher, what you're interested in, and then eventually put that all together in a coherent story, as if it was all planned from the very start as a coherent thesis. But the reality is that what you're about to see are essentially chapters in reverse chronological order. And I think that reflects a few things. That reflects the fact that Mariah has explored very different ways of working during her PhD in mathematics. Some of them with people in complex systems and data science, group project, some of them solo projects that are more mathematical, some of them an internship in sort of non-governmental organization. So very, very different ways of working, but somehow, in the last year, pulled it all together in a very coherent, almost, well, obviously a coherent thesis, but it's almost a mission statement for the field of disease modeling. So I'm really excited about the thesis that you're going to be, because it reflects a very big picture perspective of our field, thinking about models all the way down from cells and viruses to organs, to people and population. And so I think it's an exciting thesis, but it's also an exciting mission and an exciting time for the field as a whole. So, Mariah.
Thank you. Thank you all for coming. So we're going to be talking about probabilistic modeling of disease, addressing uncertainties, and within host and population level dynamics. This isn't going to work. It's fine. There. Okay, we're going to click. So we're going to start with the tool shed of modeling. This is Vermont. It looks like a barn. A lot of people keep tools everywhere. We're just going to ignore that fact. But here's the tool shed of modeling. The box isn't big enough anymore. If anyone's in the modeling sphere, the box for modeling is no longer big enough. So we have to move to a shed. So what can we do with these tools? From what everyone is pretty familiar with, we predict with these tools what future events could happen. We also challenge accepted paradigms. We explain dynamics of complex systems with these models as well. And this is something that I found math modeling, and it helped me understand the world around me. So I really enjoyed that. We also can guide data collection in new theories, along with discover new questions to ask. However, all of those are great. For this particular thesis, we're going to be talking about addressing uncertainties, specifically in disease modeling. And so a little introduction into the topics in disease modeling that we're going to be talking about during this 45-minute talk. We're going to talk about cell divisions and disease transmission. Now, the figures that I have up on the screen are representing, say, for cell division, a population of infected cells. And we can either have cells die off, or they can divide and input back into the population. For disease transmission, though, we have these different compartments, S, I, and R, susceptible individuals, infected individuals, and recovered individuals. And then there are rates saying someone becomes infected once they're susceptible, an infected person recovers and moves into that R box. And so we can define these dynamics, these compartmental models, through differential equation, through these differential equations, defining each change in these population densities. So using those equations, we can plot these figures. And so on the left, for cell division, if, say, your division rate is greater than your death rate, you're going to have an exponential growth of cell divisions. If your division rate is less than your death rate, you're going to hit an extinction, and you're not going to have any more dividing cells. On the other side, disease transmission, we can see that high susceptible count starts to decrease as as the infection spreads to more individuals, and then eventually everyone recovers from that. So one thing I thought about a lot during this was, what if the first cell or individual was removed before a division or infection? What happens if there's some stochastic extinction happening here? So those compartmental differential equation models don't capture that. They just let the dynamics occur according to the rates given. So deterministic models ignore stochastic extinction. Therefore, we move to models with stochasticity. So all the models that we're talking about have some random aspect to them to account for stochasticity. So how stochastic models do this is they use stochastic processes, particularly for this thesis. We're going to be talking about Markov chains. So we have this sequence of numbers. Say we're talking about infected individuals. We start with 1 infected individual. Some time passes. We get to 2 infected individuals, and then say these 2 infected individuals only infect 1 other person, and then that 1 person recovers, and we no longer have any infected individuals in this process. So as I was explaining that, I was saying the previous state directly informs the random variable assigned to the next state. This 1 person has the ability to infect 2 other people. These 2 people have the ability to infect multiple people, but say only one of them only 1 more person gets infected. This is known as the Markov property. And so we're talking about a chain of events, so we talk about Markov chains. So from this, the first case study defines the probability distribution of being in a particular state, say one of these particular states at time t. And for the latter case studies that we're going to be talking about today, give more detail on a specific type of Markov chain, branching processes, and we're going to get more into detail when those cases come up. So how the case studies are going to go, similar to how disease starts. It starts in an individual person, someone becomes infected in some way, and then eventually they spread into a population. So we're going to focus on an individual disease dynamics first. We're then going to be talking about population level disease spread. And these will be producing probability distributions of cumulative counts. Along with, finally, we land on this macroscopic view of disease spread and address uncertainties, not only for disease spread at the macroscopic level, but we also are going to zoom out even more to address sensitivities in just a branching process model as well. So the papers that coincide with, or the projects really that coincide with each of these, we start at the individual, go down the macroscopic level. We're going to start with the within host infection dynamics with master equations. So this first case study within host infection dynamics with master equations in a method of moments, a case study of human papillomavirus. I said we were going to be addressing uncertainties. What uncertainties are we going to be addressing here? We're going to be addressing the infection dynamics of human papillomavirus. And we're going to be doing that with the probabilistic model of master equations and method of moments. So before getting into the model, let's talk about HPV. It's an STI that can cause lesions in an epithelium. For our study, we focus on a epithelium because HPV has the highest progression rate into cervical cancer out of all other possible cancers that it could progress into. So we're looking at a cell layer, the layers within a cervical epithelium or a tissue layer right here. So how we start is we see an infection begin at the base layer. So an HPV particle comes in at this base layer and infects one of these base cells. And then it progresses and propagates through the skin through cell division. So it's not making more HPV cells other than it's just following the division process that's happening in the skin layer. So we can watch these infected cells move up through the skin layer. And eventually, once a cell dies, any virions in the cell are shed out. So throughout its process, moving up the skin layer, it's harboring more viral copies of HPV. And those get shed out and expelled. They expel infectious material into, say, the ether of the area around the cervix. So for this case study, we only focus on 1 infection at a time, but there's a possibility that these virions not only spread to other people through like sexual contacts, or it could reinfect the skin at another time. But we're only focusing on 1 infection at a time for this. So the model comes in here where we want to track the number of infected cells in each cell type over time. So remembering back to our compartment model that we talked about, those differential equations, we previously tracked probability densities. we're going to now instead track the probability of being in state S. And say, for example, state S is the number of infected cells. What's the probability of having this many infected cells? And using this compartmental model structure, we can say that there's a transition of probability between these states. So instead of having one infected cell, some transition could happen and we have 0 infected cells, or different transition probability could happen and we have more infected cells. So then we want to track the evolution of the probability of being in that arbitrary state S. So similar to the previous models, the differential equations we talked about, we use this differential equation structure. However, however, the notation that was in the compartments then moves through, and we're following the change in probability associated with that state space. All right, so for the first iteration of this model, we focused on the first 2 layers of the cervical epithelium. And the reason we do that is through literature, it came to my attention that people with cervixes or uteruses have gone through and who have gone through menopause have thinner layers of skin. So they actually don't have those top layers that would allow, say, a larger propagation of infected cells to happen. So for this particular instance of this model, we only focus on the dynamics between the basal cell layer and the peribasal cell layer, and we count dead cells. So we want to keep track of how many dead cells and possible virions come into play. And these are the parameters that explain the different division rates or transition rates or shed rates. We have a long equation that is the differential equation that explains all the dynamics happening. And we're not going to focus too much on that, but we're going to look at it visually. So what that equation is really saying is most of the dynamics and cell divisions are happening in the basal and peribasal cell layer. All these arrows are showing why things are where the probability is transitioning to. But then in the end, if you have a population of peribasal cells, they have the dynamics to shed out and become dead cells. So there's a lot more going down in those bottom layers, and then eventually those infected cells will shed out. So we had the instance where we were talking about cervical epithelium that is thinner for people who have gone through menopause. However, there's a section of the population who are infected by HPV who haven't gone through menopause. So they have a larger skin tissue layer to work with. And all the same parameters are used, except we add these transition dynamics between the peribasal cell layer, the intermediate cell layer, and the superficial layer. So there's transition happening going between those. There are no divisions that can happen in those cell layers. So these cells are just moving up the skin. Again, we have an equation that defines all the different dynamics with this, but then visually, we can see that these compartments and the transitions between them are all the same for the basal and peribasal cell. However, when we get to the peribasal cell, the intermediate to superficial, there's only one transition dynamic happening, and then eventually those infected cells will shed out. So those equations define the dynamics that we want. However, when you want to solve these, say if I want to have just for the 3 cell type case, if you want 5 infected, if you want to track 5 infected basal cells, 5 infected peribasal cells, and 5 dead cells, you have to keep track of 5 to the 3rd equations. That's a lot. And then we move on to the 5 layer, that's even more. And I'm only tracking 5 cells. There's a lot more than 5 cells in each of those layers. So this makes it really difficult to solve these explicitly. Therefore, we track the distribution of states by its moments instead. This is where the method of moments comes in. So we take the moments of all of those equations, and for this 3 cell type, we're focusing on these 9 moments. So we're dealing with the first and second moments, and so, along with those second moments encapsulate some interaction terms. Then for the 5 cell type, there's a few more, but we're not doing 5 to the third. We're not solving 5 to the third equations here. And from those moments, and don't worry, we're gonna get to some plots, and this is what's gonna be plotted. From those moments of the distributions, we can compute the cumulative probability of extinction by assuming a zero inflated geometric distribution. That really just means there's a lot of probability at nothing happens and 0, so you're at extinction, and there's a lot of probability at something other than extinction. So we can solve for the probability of extinction through that with this equation using the first and second moment of the basal cells. And then we estimate the geometric distribution parameter for the average basal cells of persistent infection. So if you're not going extinct, if your infection doesn't go extinct, then it's a persistent infection, and you want to keep track of how many infected basal cells are still in that population. And then finally, an important aspect that we want to track as well is the average cumulative virions. Assuming there's 1,000 virions per dead cell, we're going to multiply 1,000 by the dead cell average to give you the average viral output of an infection. So we're going to look at these axes. Time is on the horizontal axis. The vertical axis is the probability of extinction. And the reason there's 2 plots is because one is, we're going to zoom out and zoom in on one of them. So we can see that the time scales are different. We're going to plot simulations, the method of moments for each cell type. So here on the left, we're just looking at a time of 750. So this is in days. All of these are for day rates. We can see that the dotted lines, so the simulations and the method of moments, they validate our analytical derivations with the method of moments for both 3 and 5 cell type. They're over top of one another because the basal cells for each system have the same exact dynamics. There's no difference between them. And then if we zoom out and focus on, say, 6,000 days, we can see that the probability of extinction levels off. So at around 800 days, probability of extinction is above 55% or about 55%, while at 6,000 days, that it's around 70%. So one thing that we need to make sure we focus on is, in a deterministic model, the previous models that we talked about, the probability of extinction would have been 100 at some point. All those recovered people, we would have had a huge recovered population and no infected population. This allows for those persistent and infections that could progress into cervical cancer. So moving on to persistent infections, we're going to, over time on the horizontal, we're going to be looking at the average basals, so the basal count for persistent infections. So similar to the previous plot, we validate the average basal cells for persistent infections with simulations for both systems. And again, there is no difference between the 2 systems at the basal level because they have similar dynamics. And then finally, we can look at the average cumulative virions over time. And we begin to see that there's a little bit of a difference now starting to part between the 2 different systems. We can see that the 5 cell type system begins to diverge from the 3 cell type system. That's what this inset plot is. It's the difference between those 2 lines. And this really distills down to, for viral load, age is an important consideration when modeling HPV virion accumulation. So because of that difference, there's going to be different viral outputs for people with different ages or at different ages. And we also, we found that a quadratic equation fit the difference pretty well. We can talk more about afterwards. It was meant to be, we hoped that it was an exponential change with just the different, or the rate of the exponential being just the difference in 2 of the parameters. But I think with the multiplication by 1,000, something might have gone off, but happy to talk about that afterwards. All right, so conclusions from this case study. The method of moments is an efficient way to define infection progression outcomes. And that age is also an important factor when considering viral output of an HPV infection. Moving right along. I mentioned branching processes in the beginning of this talk. now this is the part where we get to talk about them for the next two case studies. So a branching process tracks the number of individuals in a branch over time. And similar to the number of infected people that we talked about, this branch is, say, the people who become infected off of an initially infected individual. So branching process can be defined over a network structure that can give some structure to how many people could you be possibly counting in, say, the next generation. And so, as I said before, in disease dynamics, each infected individual can infect their contact, continuing the growth of this branch. So for the first case study using branching processes, we're talking about temporal and probabilistic comparisons of epidemic interventions. We're addressing the uncertainties of temporal comparisons of probability distributions, which are the outcomes of tracking these branching processes over contact networks. And we're going to do that with probability generating functions. I unfortunately didn't have it in the title, but that's okay. So probability generating functions. We need to be, before we actually talk about the functions themselves, we're going to consider this network made up of nodes or vertices. So that's what the circles are, and edges are the connections between. And we can define this network, or a network, by its degree distribution. So its degree distribution is a probability distribution that explains what is the likelihood of having 0 contacts or 0 neighbors or 0 connections, or 1 or 2 or 3. And so we can say that the probability that a randomly chosen vertex on a graph or a network has degree K. We're going to denote this as PK. We're going to line all these probabilities up as a sequence of numbers. We're going to put the sequence of numbers into an array where the index of the probability is the same as its degree. So index 0, you're at probability of having 0 connections. Index 1, probability of having 1 connection. And so just visually what we're talking about here is also this stub list, where that's the probability of having no connections and the probability of having 1 connection, and so on and so forth. So mathematically, we want to represent this stub list in a function. So we're going to use this generating function here, and we're going to replace the stub list, this visual stub list, with the probabilities. We're also going to say that G0, we use the notation G0 because we're talking about a randomly chosen vertex. We're starting at an origin of a vertex, and we'll talk more about where other numbers come into that notation later. Now, actually getting to the probabilities, you can lay out this degree distribution and the probabilities associated with degree in this power series function, known as the probability generating function. Now, one thing that we can also do with this function that displays the contact network structure, we can decide to transmit over each contact with some probability. Say we're going to call it capital T. So of those contacts, we say infection spreads over the edge with probability T. It doesn't spread with probability 1 minus T. And this actually gives you another generating function, this Tx plus 1 minus T. And you can compose those generating functions together to say, I have a contact network, which is G0, and then we're going to say some type of coin flip. Are you transmitting or not over the edges that are connected to those? So that's transmitting over a contact network. However, we can also define the excess degree of the vertices reached when following a randomly chosen edge. So excess degree here just means I follow an edge in, what are the extra connections that are attached to that individual as well. So denoted by those red stubs on the top. And remember I said we were talking about G0 before because we were at a randomly chosen vertex. Now we're at a randomly chosen edge. So you're leading into an edge, or you're following an edge leading into a vertex. So we denote this with a G1 function. And then also you can see the edges that we're following in for all of those stub lists. And so we get this G1 by thinking about how, by following an edge is proportional to the vertex degree. It's friendship paradox. Your friends have more friends than you. So if you follow an edge to a friend, you're more likely to find a friend who has a lot more friends than you. And for mathematical purposes, we can formalize G1 through a derivative. All right, so that was a little bit about PGFs. The standard PGF framework does not keep track of time. Like there's no time element to it. So Noel et al. Expanded the PGF framework to use multiple PGFs to track the branching process on an infinite network via generations. So we're going to explain their framework and expand upon it. So what they did is we have a piecewise generating function that depends on the generation that you're in and dictates the contact. So you're either dealing with the original contact distribution or you're dealing with its excess degree distribution. And then for each generation, we are going to use this G sub G to calculate cumulative infections. We're going to do that through another generating functions because the generating function is at the end of the day, generating functions are just really good at counting. So I said we're going to incorporate G sub G, but we need to show you what we're going to end up with. This is what we want to end up with. We aim to show how the piecewise PGF defines the PGF for the probability of S cumulative infections and M new infections in generation G. So how we're going to expand this to show where the G sub G fits in. First, we're going to say we can rewrite this equation knowing that S prime plus M is equal to S. So all this is saying is the cumulative infections in a previous generation, S prime, plus the new infections are going to give you the cumulative infections for that current generation. So we're going to expand this exponent. We're going to rewrite it just a little bit to combine X and M or X and Y to have the same exponent. And now we're going to focus on, so this psi GSM explains the probability of having S cumulative infections and M new infections in G, but we can rewrite this as the probability of having S prime cumulative infections and M prime new infections in G minus 1. So we're looking at, well, what's the probability of being in the state prior to the state that we're in? But then multiplying that by, well, what's the probability of having new infections, M new infections, given the S prime, M prime state? So we transfer that into this equation. And now we're talking about the PGF of having S prime cumulative infections and M new infections in the next generation. However, we want to get down to M prime. We want to have S prime and M prime be our only counting variables. So this part of the equation describes the PGF of having M new infections from state S prime and M prime, which are generated from G sub G minus 1. And what that means is, this part means G sub G, or G sub G minus, lots of G's. G sub G minus 1 explains the contact distribution at generation G minus 1. If I say I have M prime new infections, so say M prime is equal to 1, I need to take only one G sub G minus 1 excess degree distributions and look at that. If I have 2 of them, I need to look at 2 of them. That's why we raise it to that power. So that's how we incorporate G sub G minus 1 into our counting PGF for cumulative infections and M new infections. So that was the Noel et al. That was the work of Noel et al. How can we expand this framework to compare interventions and compare probability distributions? Well, we're going to take their framework and we're going to alter the transmission expression allowing for interventions. So we're going to go from just a regular capital T to a capital T sub G. Now, to make sure that we're mapping this correctly, in continuous time, individuals can infect people past generational windows. So in order to make sure that we map them accordingly, and capture all these people who could be infected in different generational windows, we say that given the probability of infecting a single person with vaccination included is this T sub 0. So if you infect before the first generational window, that's the probability of that happening, and it gets mapped up to generation 1. If an infection happens after the generation 1 time window, we say the probability of that the next generation happened before, but then multiply that by the probability of a person being infected, so that W0T1. And then this goes on for future generations for however long this person can become infected. No matter what, all of these are mapped back to generation 1, because in a branching process, we need to keep track of subsequent generation counts. Now, I hinted a little bit at the probabilities of infecting and probability of waiting time, and how we're going to explain those is we're going to use the transmission rate between 2 individuals. We're going to use the recovery rate. We're going to use the current vaccination coverage, current cumulative vaccination coverage at G, this VG, and then the generational dependent average excess degree, this Q sub G. And we're going to be using a Poisson process. So Poisson processes, all it says is we're going to sum up all the possible rates that could happen, and whatever probability we're focused on is that rate's going to be in the numerator of this. So for the probability of a single person causing an infection with vaccination included, vaccination being the 1 minus VG section, and because this is the probability of infection, we put that beta term up in the numerator. I alluded to the probability that the next generation occurs before a given person transmits or recovers. So how we proxy that is we represent the passage of time to the next generation as beta times the generational dependent average excess degree, incorporating vaccination. So really what that's saying is if you have a high transmission rate, you're going to infect people quicker over their contact degree distribution. So that's how we account for the passage of time. And so, as I showed in that figure prior, we need to combine the probability of an infection in G along with G+1, along with G+2. So we need to account for all of them, or as far out as many generations as we want to count. So this capital TG, this transmission expression, is then an accumulation of transmitting in that generation, plus waiting a generation, transmitting in the next, plus waiting 2 generations and transmitting in the next. So that's a transmission probability, or that's the transmission term. What vaccination strategies are we going to be using to test this? Well, we can use random vaccination. This adjusts the contact distribution uniformly by a proportion. Once you renormalize, the distribution stays the same, but the idea is that you're taking a same percentage from every single degree class. And we also use targeted vaccination. So we're using degree targeted vaccination, which adjusts the contact distribution by truncating. So we're going to target the people who have the most connections. And so that's what this would look like. And then you would renormalize. All right, to the distributions. So our top row, we're talking about random vaccination. And then each column is either theory or simulation. So for a geometric distribution, we compare in the theory side, we compare a non-intervened system. So we just let the system run and we plot the dotted lines. And then we also have the intervened system, so the solid lines. And we impose vaccinations at generations 4, 6, 8, and 10. And so each line represents a different time point, different generation time. So we can see as more vaccination is imposed, the dotted lines and the solid lines begin to diverge. And the simulations validate these analytical measures. For targeted, very similar, same vaccination strategy. All of these were for a 0.5% vaccination per generation. And we can see how those intervened lines begin to diverge even quicker earlier in time. And we also have the simulations to validate. One thing I want you to focus on, though, is wouldn't you expect the non-intervened system to be above the intervention line? Currently, what we're looking at is the non-intervene system, so the dotted line, is showing lower probabilities for cumulative infections over time. Seems a little funky, right? You're intervening, you would expect less case counts. What's happening here is, so for an array of targeted vaccination strategies per generation, the probability mass is propagating in the smaller infection counts with the stronger intervention, because these distributions are hitting 0 at a certain point. So unless you spread it out over full cumulative infections, that makes it really hard to tell, well, which one is better at these low case counts. Which leads us into, well, how do you compare these distributions and these interventions properly then? If you look at a distribution, it's a little confusing. So we defined a few metrics in this work. The first metric that you can easily do is you take the average of the distribution. So this is the mean number of cases. And so what we're going to be looking at here is, these are targeted vaccinations, different targeted vaccination percentages per generation on the horizontal axis, and the y-axis is the number of cases. And we do it for 2 generational windows. So we just want to show you the temporal aspect of these vaccination strategies. And another thing that we're going to be talking about, so the horizontal axis is varying targeted vaccinations. We also are going to have these 2 constant lines of random vaccination rollouts of at 3% and 5% as well on these plots. So what we can see here is which targeted vaccination strategies perform better, worse, or in between these random vaccination strategies, and at the different time points, how much those cases vary. So if we focus on one particular point, say in generation 10, at this 0.25% vaccinated per generation, we can see that, so this is using the same scheme that we talked about before. So there's 4 rollouts. So this means this purple dot is representing, at generation 10, it's representing 1% of the population was vaccinated. And it is at even with the random vaccination rollout of 3%. So, and that's 12% of the population that has been fully vaccinated. So we know targeted vaccination performs much better when you target people with higher degree. But another thing to focus on here is at generation 5, the 3% random vaccination is much lower than the 0.25 targeted strategy, but then they even out. So this temporal aspect really does matter. We only don't want to be looking at one potential window that we want to mitigate for. So that was average cases. Similarly, we can do this for what we call PG flat. It's critical level cases. People we associated with it with flattening the curve. So this is the probability of being at or above a critical level critical number of cases, and we set that threshold at 500. All this means is on your probability distribution of cumulative case count, you're looking at 500. You're going up. You're seeing what probability that lands at on that distribution over time. So the vertical axis is in probabilities, not in cases anymore. But similar trend to the previous one, where we see the random vaccination rollouts begin to catch up with each other over time, and we still have a downward trend of the strongest targeted vaccination strategy still performs the best, along with the last 2 targeted vaccination strategies perform the best. So conclusions off of this. PGFs, or probability generating functions, are powerful tools, and this framework distills their outcomes into easily comparable metrics, along with the quality of targeted interventions depends on what is being mitigated and at what time. So those metrics give people options, say decision makers options to say, well, what do we want to mitigate for and at what time? And then they can dictate the best intervention strategy. All right, finally, we're talking about the uncertainties around a particular PGF outcome. And so we're talking about the sensitivity analysis of stochastic polynomial roots. And as I alluded to, we're going to be talking about probability generating functions in this instance. So this is our final macroscopic zoomed out sensitivity analysis of how this framework gets used for epidemiological forecasting. Excuse me. So within PGS, we're going to be talking about giant component analysis. So this network shows a disconnected network. So this person, so say the single individual, the single node can't reach everybody else. So say they were isolated. They define one component of this network. Same with that other cluster. So we can use PGFs, where again, they're just counting tools. We're going to use PGFs to define the distribution of sizes of components reached via a randomly chosen edge. And we're just going to say that this does not include the giant component. On a PGF, if you wanted to count the probability of being of size infinity, because that is what a giant component is, we can't do that. Like we don't have an exponent to an infinity, like how I like to think about it. So we're going to be talking about H1, and again, it's in 1 because it's reached via a randomly chosen edge. We're going to think about it visually though. So we have H1 to be the distribution of component sizes when following a randomly chosen edge. So the square here represents the possible component size that comes from this. Now, all these possible component sizes are a compilation of following a randomly chosen edge to a vertex. No matter what, will reach a vertex, but then its distribution or say its excess degree will vary. And then connected to that excess degree is more component sizes. So we define this self-consistent equation, this H1 x G1 of H1. So again, composition where the G1 is moving towards, and say exponentiating this H1 depending on its edges and its excess degree. The extra X there is because we don't count components of size 0. We don't have a constant term in this PGF. That's how I like to think about that one. Similarly, we can do this for H0, and that is just the distribution of component sizes when randomly choosing a vertex. So it has the exact same structure, except because we're following an edge into the component size, we use H1 inside of that composition. All right, so that was for finite size components. Now we're going to talk about the giant component. How do we figure out what a large proportion of the population, say, becomes infected through a disease? So our giant component size, we're going to remember that H1 and H0 is the distribution of component sizes excluding the giant component. So because it's a probability distribution, when we plug in 1 into this H0 function, we get this proportion where S is the fraction of the network that is the giant component. So we have the 1 minus S because that's the part that's missing from that generating function probability mass. So then, similarly, we can plug 1 into H1, and we have that U is the probability of following an edge that does not lead to the giant component. We plug 1 into our self-consistent equation. We then can achieve this G1 of U equal U, where U is the probability of following an edge that does not lead to the giant component for the excess degree distribution. And where this gets us is that we can solve for the probability of choosing a vertex in the giant component S when we, using the solution U in G0. However, for the purposes of this project, we assume that the original degree distribution and the excess degree distribution are the same. So we're going to say that G0 of U is equal to G1 of U. And then that makes solving for the fraction of the graph that is the giant component much easier, where it's this root U. So when we solve this, it's a polynomial root U that is 1 minus the root, then gives us the fraction of the graph that is the giant component. So for a negative binomial distribution, what does this root U mean? And what is, say, the outbreak size or the fraction of the giant component fraction mean? And these negative binomial distributions are parameterized with mean and dispersion parameter. So the dispersion parameter just, you have a more homogeneous system, so that they are more similar to each other with higher dispersion. And then lower dispersion is a more heterogeneous system. So people are not like each other. And then on the horizontal axis, we have the average secondary cases. So from here, we can see that for differing R naught and in this case, we used alphas. For differing R naught and alphas, we get different root values of this polynomial, which then correlate to different outbreak sizes. So in order to test sensitivity of this, say we're testing the sensitivity of that root U, and it's ostensibly the sensitivity of those outbreak sizes, we're going to take an example of negative binomial, secondary infection distribution. We're going to determine the polynomial coefficients from that distribution and place it into this PGF. We're going to add error to those coefficients. We're going to perturb that distribution to see how much does that change our root value and our final outbreak value. And then we're going to solve this self-consistent equation and solve for that root value U, which then will give us the perturbed final outbreak size. So that's how we're going to do this. We're going to check the variances of that, but also condition numbers are a commonly used like linear algebra tool to assess sensitivity of a system of noise. So we're going to use a condition number for this polynomial and assess its statistical condition estimator to define the sensitivity of those polynomial roots. And so how we do this is, so our x tilde is going to be the perturbed root, so the root that comes out of the perturbed system, and we're going to subtract it from the true root, and then we normalize it by that root. So if you have a small root and a small difference, it's going to be normalized by the size of that root, also multiplied by this delta variable, which is just meant to say in that framework, we're assuming that perturbations are approaching zero, so they're just really small. So we just have to multiply by, or rather divide by a really small delta. So we're going to compare the condition numbers to the variance of those perturbed polynomial roots. We're going to see a grading scale where the large value means, or large darker value means more sensitive, smaller value means less sensitive for your dispersion parameter and the average secondary cases. Now, they validate each other pretty well. One thing that it might look familiar is that they follow the same contour lines as the outbreaks that we saw prior. So this is really exciting because this is saying that this really small root value, or sorry, this really large root value of 0.97, which correlates to a 0.025 outbreak, so a really small outbreak, appears to be the most sensitive from this condition number. And so if we focus on the varying of dispersion, so homogeneous versus heterogeneous, we can see that R naught equals 1 is a common threshold that an epidemic could outbreak from. If you have more than an if you have an average secondary case of 1, you're going to continue spreading the disease. But with varying heterogeneity or homogeneity between the number of contacts you have, we can see that the darkest line follows up not no matter what, but for higher dispersion parameters, we're having a very sensitive system right around 1, which is what we would expect. However, something that's also important is even if you have a high secondary case value, for really, really heterogeneous systems, there's still some sensitivity around that root that we need to be aware of. And if, say, you know that your average secondary case is 3, but you know that your system is very heterogeneous, you're still gonna have to deal with some possible sensitivity here. The final conclusions on that is testing this model makes it more interpretable, and the smallest outbreaks are the most sensitive from the analysis we did. And then this work lays the foundation for sensitivity analysis of other PGF epidemiological outcomes. Sensitivity analysis really help us understand the bounds of our models that we use, and if we want to be accurate predictors, if prediction is your goal. All right, back to our tool shed, back to our toolbar maybe. We've addressed the uncertainties with 2 different models, along with expanded their uses in 3 different cases. The first being the method of moments tracks the stochastic nature of HPV infections, which provides a framework for general cell division dynamics, infection progressions, and informs viral load prioritization, say for population models. Imposing intervention strategies on time-dependent PGFs compares the quality of interventions depending on what is being mitigated and at what time. And then finally, the condition numbers of PGFs representing network structures inform sensitivities around outbreak thresholds. So all of that work, there's also some more work that we could be thinking about. For example, a multi-scale model with the within host and population level dynamics. So case studies 1 and 2, we could combine to say, all right, well, we can inform some viral load, or we can inform the viral load through the transmission into the transmission rate of the second model, which is age dependent. We can also think about the probability of extinction informing recovery rate. However, if an individual does not recover after a certain time, then you could inform their transmission with those persistent infections that we talked about. Along with the temporal and probabilistic comparisons would then simulate these dynamics in a population, and maybe you could even compare interventions, say, for HPV. And then also another thing that I've been thinking about is off this last project is sensitivity analysis of branching processes. Like how do perturbations of different magnitudes at other times affect outcome regimes? So if you're thinking generally of models that use branching processes, they are inherently random, but what error could make that big of a difference to, instead of just perturb you within a regime, to shot put you into an entirely different outcome regime? A little something to think about. I want to thank you for listening to me talk for almost an hour, and thank you to my advisors and committee members for taking the time and reading everything that I wrote. My co-authors as well, wouldn't be here without them. And then lab mates, colleagues, Quest community, family, friends. Not everyone is pictured here, but along with everybody on the Zoom call and who decided to be here, I appreciate it. Also, if you see me cry at all throughout any point in this day is happy, and that is how I relieve stress. So don't worry about it. But I want to thank you for taking the time. And this is my visual version of my contributions to all knowledge.
We have time for questions. I'll just repeat quickly. People online, feel free to use either the chat or to raise your hand, and I'll moderate online questions. People in the room, use your physical hand. Yes, right.
Hi. I'm getting emotional. I'm so proud. So this is stellar, and I know you have a wonderful next job set up that's really continuing some of the aspects of this work. And so I'm curious, what are you most excited about this work and the methodological advancements you've been doing here and bringing them into this next role? That's just very fancy new job.
Yes. So for those of you who are maybe not aware that Brenda's alluding to, I have a position at the MOBS lab at Northeastern within the Rue Institute in Portland, Maine, working with, I believe Guillaume is probably on this call, fantastic scientist who is also a derivative of the U Laval group and PGF proteges maybe. And so a lot of the probability generating function work that I talked about will be continued on with that. Some thought processes there is, instead of doing generational time, how do you work into continuous time, which a colleague of ours, Andrea Allen, who I was also co-author on a paper with her for work similar to chapter 2 or section 2 of this talk, compare generational time to continuous time, but how can you get PGFs to actually do continuous time modeling? Along with, I would love to bring the sensitivity aspect chapter into the second case study with temporal comparisons. What part of a GF are you perturbing the contact distribution? Are you perturbing the actual probability of getting to a certain number of cumulative infections and new infections? Like, that is a whole space that has yet to be expanded. And I remember Laurent mentioning the sensitivity project to me very early on in my PhD. As he said, my chapter's a little bit backwards in chronological order. No one's thought about the sensitivity of these things and like, how can we even assess that? So that's a huge area of research for that. So I am excited about that.
There's a question online. Andrea has her hand up. She had her hand up before you just mentioned her. Andrea, if you can unmute yourself, it's nice to have you back.
Andrea.
Hi, thanks for noticing that detail of me putting my hand up first, so I don't seem too self-involved. But thanks, Mariah, for this amazing presentation. I just was wondering if you could briefly go back or just go over the different kind of summary statistic options for capturing that stochasticity of spread, and then kind of the pros and cons of using things like the average of the distribution versus some other kind of way to capture it, and what that would tell someone, but then also what it leaves off, depending on kind of which metric you choose.
What a great question. Scroll up to it. So yes, I only mentioned 2 of them. We did, it's not showing what I'm seeing, sorry. Was like, yeah, you can see what I can see. This way, this way, this way. Can everybody online see this?
Yes.
Okay, cool.
Yes.
Perfect. So for this case, yeah, we talk about average cases. We talk about a critical level of cases. So that was the flattening the curve. We also talk about, is there a probability threshold that you want to stay below, and what cases, what number of cases are associated with that probability that we want to stay at or below, along with minimal effect intervention. So comparing an intervene system versus the intervene system, like what is the chance that the non-intervene system like does better, has less cumulative counts than say like an intervene system. So averages are great if you want a single value out of a distribution. However, as you probably were alluding to, our distributions could be super large, like very variable, and the average captures just the middle, or like the where everything propagates. Or so these heavy-tailed distributions aren't really captured that well with these averages. So there is that possibility that your epidemic lands in that outer range where it's much higher than your average case count, and you try to mitigate for an actual particular number of cases. So that's something to be aware of. The other thresholding ones, for the thresholding metrics for cases and probabilities, it can say, well, if you want to mitigate cases, yeah, what if that gives you an exact chance of when would that happen? And that, for especially like flattening the curve rather than focusing on average cases, can give you a better understanding of the likelihood of that instance happening rather than the average value, and things of that nature. That was a great question. There's definitely more comparing all of them, but for the 2 examples that I talked about with everybody, that would be one comparison.
Great. Yeah, thanks so much.
Questions? Yeah, Jeremiah.
Yeah, so I'm not exactly an expert in math, so forgive me if this is a newbie question. When you talked about the state space equations and having to deal with many of them, so I was wondering, are there any numerical methods one could throw at that, and at what cost? So that's the first question. And the second question is a follow-up to that.
Okay.
Can AI help with that?
Ooh, great question. So in terms of numerical methods, so when we, here, I can scroll up to it. So I just want to make sure we're talking about this correct spot. Probably right around here, right? This one?
There's one where you had a number of.
Oh, all of
stats
them.
on,
Yes.
Right.
So again, this is a very large figure trying to explain the dynamics. For numerical methods for this. Oh, to say mitigate this problem.
Yeah, exactly.
Okay, to mitigate this problem. Numerical methods. Well, so one aspect of this is I'm using explicit master equations. There's another variation master equations called approximate master equations, which that help with the computational expense of what I was explaining. In order to just keep the system exact, I kept stuck with explicit master equations, but definitely would be something to think about if you didn't exactly care about keeping your methods exact for this application to go to approximate master equations. AI, machine learning. I haven't thought about it, and I feel a little bit removed from the machine learning aspect of this. But I think that would be a great talk that we could chat about that part.
I usually shut up during this part, but I mean, you could try, like, the way you solve this problem is with the method of moments.
Yeah.
I wonder if you give the explicit master equation and you ask, some AI model.
Yeah.
Apply the method of moments, is it gonna give you the same equation?
Hmm.
That would have saved you, like,
Yeah, okay. For anyone who didn't see me writing out all the method of moments, that honestly, I really enjoyed. That's the mathematician in me. I sat at a board, or rather, we've moved over to iPads, but I sat on my iPad and I just wrote out long form equations, and it was fantastic. I loved it. So yes, we could do that. However, the joy I found in that, I'm gonna stick with that. If we had to go into higher moments, I think then maybe I'll defer to method of moments in AI, but yeah.
Any other questions in the room?
So the second case study, I think it's so neat, and you're able to assess these interventions of random rollout or targeted vaccination. How extensible is the temporal PGF framework to looking at other kinds of interventions? I mean, do you see this as being like a policy toolbox for people to assess?
Totally.
As opposed to running a bunch of database models or something like that?
Great question. So, it's definitely talked about in the paper associated with this work, but we only chose to, and again, I didn't get into the details of random vaccination, targeted vaccination. But targeted vaccination, you're updating your QG. So you're updating your average excess degree over time because you're altering your degree distribution. So you need to update the average excess degree. In your random vaccination, you're updating this VG. So you're updating the percent that you're applying to all possible transmission rates. For other types of intervention strategies, say like a therapeutic or something, that would be affecting your gamma. That would be affecting your recovery rate. Or if you have masking interventions that say this VG could also act as something for a masking intervention or some other type of thing. So all these parameters can be altered depending on different intervention questions. For this work, we only focused on 2, but there are other areas to work within. Again, probably outside of just these parameters, but our initial thought process was these parameters can all be considered generational and altered accordingly. So one thing I thought about, this is a little tangent to your question, but what happens if we're not intervening? What happens if we're dealing with a more virulent strain? Or what happens if people are doing, say there's isolation and I can't think of the word right now, shutdowns of everything. What happens if everybody goes back out into the world and starts interacting again? And that situation could be modeled by the excess degree distribution is changing. It's not being dampened, it's being expanded. So there's a lot of flexibility in this transmission term with different intervention strategies and non-intervention strategies.
One final question, right?
Yeah, building up on Will's question, I love that question, Will, and I also was thinking about similar things here, of testing different interventions, and I think this is super powerful work. And I'm curious, in terms of the computational intensity or the load or like the heaviness of this,
Mhm.
is there a way to make it some sort of like online dashboard or something, or have you
Mm.
created some sort of system to allow others to play with these different variables and kind of test these different
Yeah.
interventions in that way that Will maybe described it, like there's decision makers, like
Mhm.
you mentioned, or policymakers?
So currently, all the data for this code sits on a desktop in Tiger, which can be much more of an improved system of how we model this. That was also simulations take a lot longer than the analytical aspects of this, which is important to know. Dashboard, I haven't thought of it. I know there's a lot of dashboard lovers here. So Jonathan is not here, but maybe I can be taught. And along with, I know the Mobs Lab is where I'm headed. They do a lot of dashboards for a lot of different people for the Gleam model that they have. So I think that would be a great tool. I appreciate you asking the question. I have not set up the infrastructure to let people play around with this. I do think targeted vaccination and random vaccination, there's a little bit more of methodology under the hood that I didn't show you, that would have to be worked out, and we would, in order to facilitate a more widespread dashboard, would probably have to work out the kinks and work out the math with different intervention strategies and how that math would then filter into the PGFs that we use. So more work to do, but definitely some cool stuff to come out of it.
Okay, I'll just end the public portion of the Q&A by saying that Mariah has been part of other projects
Yes.
during her time here that were not presented. So if you see her later today, continue the questions and ask her about these other projects. But for now, let's just thank her for the presentation.